This video goes over question 19 of the exponential and log functions assignment. A formula for the relationship between weight and blood pressure in children is given by the formula below, where P of x is measured in millimeters of mercury and x is measured in pounds. Use the formula to answer the questions. What is the rate of change of blood pressure with respect to weight at the 60-pound weight level? The rate of change at the 60-pound weight level is approximately blank millimeters per pound of change. Do not round the final answer, then round the nearest to the nearest hundredth as needed. So the first thing I'm going to do is rewrite this function and distribute the 18.6. P of x equals 18.6 times 5 plus 18.6 times the natural log of x. Well, 5 times 18 is 90, and then 5 times 0.6 is 3, so it's going to be like 93 plus 18.6 times the natural log of x. But either way, this is just a constant. So when we take the derivative of this pressure function, blood pressure function, the constant's going to go away, and I'm going to get just 18.6 divided by x, and that's going to be millimeters of mercury per pound of change. And we can go to the calculator and get that. So I'm going to go to a calculator page and put in 18.6 divided by 60. There's already a decimal point in there, so I'll get a decimal answer, and we're supposed to round to the nearest hundredth, so 0.31. Check answer. Well done. What is the rate of change of blood pressure with respect to weight at the 80-pound level? So we'll go put that in, just change the 60 to an 80, and 0.23 rounding to the nearest hundredth. Check answer. Nice work. And I'm going to show you how to do this another way in the calculator and show you something interesting about the endpoints. So I'm going to go back to the calculator and go to a graph page and put in this function. 18.6 parenthesis 5 plus control e to the x gets me natural log of x. And then I'm going to put in the domain restriction. Control equals such that I'm going from 10 less than or equal to x less than or equal to 100. So I'm going to hit enter, and I don't see anything. My window's not great, and I'm going to go to the calculator page and do f at 10. So 136, and then f at 100, 178. So I know where to set my window in the graph. Menu 4, 1. I'm going to stick with negative 10 and then go like to positive 110. So a little bit of extra room, go by tick marks every 10. I like to see the y-axis, so I'm going to go like negative 25 to 200 and go by 20s. So there's my logarithmic function, and I can get the derivative out of the graph. Menu, 6 for analyze graph, and then 6 is dy over dx, the derivative. So it says position. So the first one I want is at 60. And there's a little block here with a 60 in it that you can't see. Enter. So 0.31. Yep. And then menu 6, 6, 8, 0. And here we can see the little box. Enter. And 0.23. So we got that there. Now I did another version of the problem where it said, what is the change in blood pressure per pound at 100 pounds? Well, if you remember, we cannot take the derivative at an endpoint. So these endpoints are 100 and 10. So if I go menu 6 and try to put in 100 and hit enter, the calculator correctly tells me that that's undefined. Same thing at 10. The calculator will say it's undefined. Now, could we evaluate this expression at 10 and 100 and get a number? Yeah, we could. But it's kind of a little error in the book in the different version of this problem. But we did get both parts of this problem correct. That concludes this video.